Hello, everyone. It is Mrs. Treese, and I'm going to go over titrations with you guys. Today, we are just going to talk about titrations between a strong acid and a strong base. And then next class, we'll kind of talk in and jump into, well, how is that different than when we have a weak acid or a weak base in a titration? So we're going to start nice and simple with just strong acids and strong bases. So starting off, what is a titration? Basically, when we are doing a titration, we are trying to figure out the concentration of an unknown solution. We should know if it's acidic or basic, but we don't know its concentration. So there's two parts to this. In order to do that, number one, we need a titrant, our titrant. And that is the solution that we know the concentration of. So if our unknown is a base, then our titrant would be an acid. If our unknown is an acid, then our titrant would be a base. And it's going to go in our burette. A burette is essentially a long kind of tube, and it has a stopper at the end so that we're able to release it. It's marked in volume increments so that we're able to tell how much we've let into our solution there. Yes, it has a stopper so we can open and close it, and we can control the flow of how much goes into our solution. All right, our titrant is added to our solution of unknown concentration, basically until we see it being consumed. And we're trying to get to what we call our equivalence point, and our equivalence point would be where our hydrogen concentration is equal to our hydroxide concentration, and so we have that nice neutral solution. All right, we plot that on what we call a pH or titration curve, and it basically is a plot of how our pH changes as the amount of titrant is added. So over here, we have right there, that is a picture of a titration. So in this case, we have a strong base in our burette. We would know the concentration of that base. We have a strong acid right there. And then this would be our titration curve. So as we add our base right here, this is our titration curve. As we add our base, we keep going until we get to this place right here where our pH is about 7, and that's what we call our equivalence point. So our equivalence point would be point S right there. And then again, if you add too much of your titrant, then it'll go and it'll become basic or acidic, whichever one you're looking at there. Okay, so then the question is, well, how do we know that when we've reached our equivalence point? And we know that because we have acid-base indicators. So we use an acid-base indicator. And we try to get to the end point. The end point is going to be where our indicator changes colors. Now, there's a lot of different indicators that we can choose from. Most commonly, we use something called phenolphthalein. Phenolphthalein is clear whenever it's actually an acidic indicator. Most indicators are acidic. And so it's clear whenever it has an acidic pH. And then as soon as it turns basic, it turns pink, hot pink. And so we try to get it to this point where it's kind of this light pink that's going to be really close to our pH of 7. And that's how we can tell that we're at our endpoint, is through our indicator. So we do have to be careful when choosing an indicator because we want the indicator endpoint and the titration equivalence point to be as close as possible. So we want to make sure that we are getting as close to that like 7 neutral pH as possible. Now, we really only get to that 7 neutral pH when we're adding a strong acid to a strong base, but we'll talk more about that later. So, since strong acids and bases have a large vertical area, color changes are going to be sharp, and a lot of indicators can be used since we're going to have, we have this like long area right here where we have like that kind of equivalence point where we add the acid and base and we don't have a lot of pH changes. However, when we have those weak acids or bases, we have to be more careful in what indicator we choose. So since indicators are normally weak acids, they'll have one color in their acidic form and another in their basic. Like I said, phenolphthalein, colorless in acidic form, basic pink in its basic form, and it changes in the range of 8 to 10. So it's really close to that equivalence point. Typically, to actually see the indicator, 1/10 of the initial form has to change before we actually are able to see that color change. And so to be able to figure out which one we need, typically the useful range of an indicator is its pKa plus or minus 1. So basically we want to determine the pH at the equivalence point of the titration and then pick an indicator with a pKa close to that. So most of the time we're going to use phenolphthalein, but just know that you can use different indicators depending on what you like, which acid and which base you're using, as well as what the equivalence point of that one is going to be. Okay, so today, like I said, we are just going to talk about strong acids and strong bases, all right, and their titrations. So these are easy because all of our reactions are going to completion, as in all of our acid completely dissociates, all of our base completely dissociates, so the reaction goes all the way to completion, and it should form a neutral salt as well. And if we do reach our equivalence point, our solution should be neutral. Like I said, when we have weak acids and a strong acid, a weak acid and a strong base, or a strong acid and a weak base, at our equivalence point, we're going to be slightly acidic or slightly basic. So, let's jump in and see what we've got. All right. So this problem says 100 milliliters of 0.1 molar HCl is titrated with 0.5 molar NaOH. Calculate the hydrogen ion concentration after 50 milliliters of base has been added. Okay, so the first thing I want to do is we do need to figure out, well, how much hydrogen do we have and how much hydroxide do we have? But kind of the first thing I want to show you guys is I do want to show you guys that net ionic equation and what's actually going on in this reaction. So essentially what we have is we have hydrogen, HCl, plus NaOH. This would be a double replacement reaction. It's a neutralization reaction as well, so which is just a special type of double replacement, if you guys remember. But what we're going to have is we're going to form water and that salt. So that salt's going to be NaCl. All right. All of these are soluble except for the water, which is water. So basically what ends up happening in our complete ionic equation is we have H plus Cl minus plus Na plus OH minus yields H2O is not going to break apart plus Na plus Cl minus. All right, so we'll cross off what's on both sides. So Na and Cl are on both sides exactly the same. And we're left with our net ionic equation being that our hydrogen plus our hydroxide yields H2O. Okay, so I don't really care about the sodium and the chlorine because they're not actually participating in the reaction. They're just spectator ions. All right, so this is my net ionic equation. All right, and I just kind of wanted to show you guys how that is derived and just make sure we understood that in a strong acid, strong base, this should always be your net ionic equation. H plus OH yields H2O. So strong acid, strong base, that should be your net ionic. Okay, so first thing we need to figure out, though, is we need to figure out how much hydrogen and how much hydroxide are we actually using in this reaction. All right, now, these are both strong acids and strong bases, so they are going to completely dissociate. So if I have 1 molar of HCl, that means I have 1 molar H+. All right, and so I need to figure out, essentially, how many moles of H+ I have. So I have 1,000 milliliters, which if I can, 100 milliliters, which if I convert that to liters is 0.1000 liters times my molarity, because to get to moles, it's just molarity times liters. So times my molarity, which is 1.0 molar, which gives me that I have 0.100 moles of hydrogen. Okay. Then I need to do the same thing with my base. So I have 50 milliliters, which would be 0.0500 liters of base times the molarity, which is 0.5 molar. So when I solve that, I get that I have 0.0250 moles of hydroxide. Okay, so now what we're going to do is we are going to make a BCA table. The BCA is before, change, and after. It's basically a rice table with just slightly different naming on it. All right, so our net ionic equation is that our hydrogen plus our hydroxide is going to form that water. So before my reaction takes place, before I've actually added this, I had 0.100 moles of hydrogen. I don't need to write the of hydrogen, but I had 0.100 moles there. And then I had 0.0250 moles of hydroxide, and I should have no water before my reaction takes place. All right, now then my reaction is going to take place. I have less hydroxide here, so essentially that's going to be completely consumed, all of my hydroxide, just because I have less of it. So my change is going to be that I'm going to subtract 0.0250 moles of hydroxide. Because this is a 1-to-1 ratio, that's also how much of my hydrogen is going to be consumed. And then that's how many moles of water we are going to produce. All right. So then after, just subtract them. 0.1 minus 0.0250 gives me 750 moles of hydrogen. Should have consumed all of my hydroxide, and then I have 0.0250 moles of water. All right. So this is how many moles of hydrogen I have afterwards. It wants us to find out what our concentration of our hydrogen would be after our base is added. So what we're going to do is this is how many moles of hydrogen we have. So we have 0.0750 moles of hydrogen over, to find out our molarity, it's moles divided by liters. So over our volume, which our volume is going to be the two volumes added together. So I had 0.100 liters of my acid plus 0.050 liters of my base. So add those together and solve it up. Go ahead and plug it into your calculator. And we should be left with 0.500 molar hydrogen ion concentration. Okay, so really these don't involve a lot of stoichiometry. It's just looking at this BCA table and figuring out which one's completely consumed. All right, let's do the next one. So kind of going off the same problem, let's calculate the H plus instead of after adding 50 milliliters of base. Now let's do it with 200 milliliters of base added. All right, so we should already know our hydrogen ion constant, or our hydrogen. So we have, from our first one, we had 0.1, oh my goodness, I don't know why I'm struggling so much with my words, 0.100 moles of hydrogen. Again, just got that from our first problem. We're not changing our hydrogen concentration because that's what we've got. But instead, we are now talking about, we're changing our base. So for our hydroxide, to figure out how many moles of hydroxide we have 0.200 liters times our 0.500 molarity. Wow, I really don't know what's wrong with me, guys. So 0.2 times 0.5, so that should give us 0.1. Oh my goodness. 0.100 moles of hydroxide. Okay, so now let's do our BCA. So our net ionic, again, because it's a strong acid and a strong base, is that H plus OH minus yields H2O. So before our reaction takes place, we have 0.100 moles of hydrogen. We also have 0.100 moles of hydroxide, and we have no water. All right, those are both even, so one is not more than the other, so we're going to subtract 0.100 from both of them. So for our change, both of them are going to lose that much, and then we should make 0.100 moles of water. So after we have 0 hydrogen, 0 hydroxide, and 0.100 moles of water. Now guys, our H plus is 0 here. However, is our H plus 0 in our solution? No. So our hydrogen ion concentration is not 0. So where's our hydrogen coming? Where's that hydrogen coming from? If it's not 0 and we've consumed all of our acid, where's it coming from? Well, guys, there's water here. And the hydrogen ion concentration of water, of pure water, is 1.0 times 10 to the negative 7th. So again, because our hydrogen should equal our hydroxide and we've made all of that pure water, our pH will equal 7. So our hydrogen ion concentration should be equal to 1.0 times 10 to the negative 7th molar, because again, we've consumed all of our strong acid and all of our strong base, so we're left only with water. So our hydrogen ion concentration should be equal to the hydrogen ion concentration of water. So it's not 0. Our hydrogen ion concentration is 1.0 times 10 to the negative 7th. All right. Okay. So now I want you guys to try the last one. It's after 300 milliliters of base has been added. So you guys go ahead and try it, see how it goes, and then come back and we'll go over it. All right, let's go over it. So once again, we're starting with 0.100 moles of hydrogen because we're just going from that initial problem. We're just now calculating with more base being added this time. And then for our hydroxide, we had 300 milliliters, so 0.3 liters times our molarity gives us that we are starting with 0.150 moles of hydroxide. So our initial or our before of our hydrogen is that we have 0.1 moles. We have 0.150 moles of hydroxide, and we should have no water. Now, how much is going to react here? It's a 1-to-1 ratio. We only have 0.10 moles of hydrogen. So since we only have 0.1 moles of hydrogen and we have 0.15 moles of hydroxide, our hydrogen here is our limiting reactant. So that will be our change. So only those 0.1 moles of hydrogen are going to be able to react. So we'll subtract both sides by that, and that's how much water will be produced. So we should have no hydrogen from our acid anymore. We should have 0.05 moles of hydroxide and then 0.1 moles of water. So basically what's significant here is our hydroxide ion concentration. So because it's we've added more base than we had acid, then it's going to be a basic solution. So I have 0.05 moles of hydroxide over my total volume now gives me that I have a 0.125 molar hydroxide solution. Now it wants us to calculate the pH. So since I have my hydroxide ion concentration, I can actually solve for my pOH. So pOH is equal to the negative log of our hydroxide ion concentration, which is 0.125. which gives me that I have a pOH of 0.913. pH plus pOH should equal 14. So pH is going to be equal to 14 minus 0.913, giving me a pH of 13.097 here. Because again, our hydroxide is our significant, is where our pH is going to come from because we have more hydroxide than hydrogen. So we have a basic solution here. All right, that is titrations part 1, guys. Next class, we'll go over the second part of titrations with weak acids and weak bases. All right, have a good day. Bye.